Electronegativity and bond polarity. Well, these dots, as you might guess, are a simplification. In fact, the electrons are not always shared equally, just like people don't usually share things really equally, right? And so what we have with unequal sharing is what's called a polar covalent bond. And this is between an ionic bond and a pure covalent bond. So a pure covalent bond has the electrons being shared exactly equally. An ionic bond has one atom giving the electrons to the other. And in between that, you have polar covalent bonds. So the electrons are being shared, but not equally, right? If we look at a molecule like hydrogen fluoride, we have several different depictions of it here. If you have hydrogen fluoride gas and you apply an electric field to it, we can observe that the molecules align themselves with the electric field. This tells us that they have a positive end and a negative end. And they do. And the reason is that fluorine is a big old electron hog. Fluorine hogs the electrons that are shared, and so this molecule is not balanced electrically. And there are different ways of indicating this. We can use an arrow notation, where the arrow points to the more electronegative element, and there's a plus sign at this end. Or we can use the Greek lowercase delta. And so this is a partial negative and partial positive and a partial negative charge. It's not a full plus and minus like an ion. It's partial. Like, maybe half a charge or 0.3 charge or something like that. I can't remember. Okay, well, we'll go with this. So what we call electronegativity is the ability of an atom to attract electrons to itself in a chemical bond. And it's inversely related to atomic size. And so what we find is that fluorine is the most electronegative element. If we look at the periodic table, what did we learn about trends in ionic sizes? In atom sizes. As you go across the period from left to right, they get smaller, right? And as you go down a group, they get larger. So leaving the noble gases out of it, because they really don't form bonds, who's the smallest element? Fluorine. He's the smallest. He's the most electronegative. He has the most attraction for electrons in a bond. And here's a table that shows the different electronegativities. And here's hydrogen over here being kind of an exception to everything. But generally we see a trend that as you go across, electronegativity increases, and as you go up, it increases. I find this trend to be easy to remember because fluorine is the most electronegative, and so if you're closer to fluorine, it's more electronegative, and if you're further away, it's less. So when we talk about bond polarity, the degree of unequal sharing is going to depend on the difference in electronegativity. So delta En, delta meaning difference, En short for electronegativity, because that's a really long word. So delta En. And the divisions here are arbitrary. So if we have zero difference zero difference in the electronegativity between the two atoms, then that's a purely covalent bond. But we go up to a difference of 0.4, and we say, well, that's we're going to call that a covalent bond. That's equal enough sharing. And if we go over here, if we get a difference above 2, then we say, well, that's really a transfer of electrons, and that's an ionic bond. And then in between, the electrons are being shared, but they're not shared equally. So that's a polar covalent bond. And if we go back and look at this, one important pair is carbon and hydrogen. What's the difference in electronegativity between carbon and hydrogen? 2.5 minus 2.1 is 0.4. And on here, 0.4 would qualify it as a nonpolar covalent bond. That carbon-hydrogen bond, really, really common in organic chemistry. And so when you see just carbons and hydrogens, it's nonpolar. There are some other ones here that are the same, like carbon and sulfur. But for the most part, the ones we're going to run into, just kind of as a general rule of thumb, if the elements are different, it's pretty safe to assume that it's a polar bond. If the elements are the same, obviously, it's a nonpolar bond. And you do not memorize electronegativity values. So if there are questions about whether it's nonpolar, polar, or ionic, if you're given electronegativity values, then you can use that to determine whether it's polar or nonpolar or whatever. But what I think is the most important is to be able to just use the periodic table. So ionic bond, metal, nonmetal. It's going to be ionic. Nonpolar covalent bond, carbon and hydrogen, or any two identical elements, like Cl2. Chlorine and chlorine, it's the same element. They've got to have the same electronegativity. And if you've got different things, like carbon and oxygen or something, then you could probably assume that it's a polar bond. Okay? So what a dipole moment, they use the symbol mu. Dipole moment occurs when there's a separation of charge, positive and negative charge. And so mu is equal to Q, the magnitude in charge, times R, which is the distance between them. And the common unit is dBi. This is a little important thing. I really don't care about this. Sorry, Mr. dBi. But anyway, so if we look at Cl2 molecule, the difference in electronegativity is 0. Its dipole moment is 0. Chlorine, fluorine. The difference in electronegativity is 1.0. And so we find that the dipole moment is 0.88. So the difference in electronegativities is related to the strength of the dipole moment. There's hydrogen fluoride is 1.9, dipole moment 1.82. Lithium fluoride, 3.0, 6.33. Because lithium has a lower electronegativity than hydrogen does. We can talk about percent ionic character, the ratio of the bond's actual dipole moment to the dipole moment it would have if it went ionic. No bond is 100% ionic. If it's greater than 50%, we consider it to be ionic. So if we look here, down here under 25% ionic character, all of these are nonmetal. And up here, these guys, with the exception of hydrogen fluoride, which is still under 50, all of these guys are metals and nonmetals. So they fall into the ionic camp, I guess. Okay. Determine whether the bond formed is pure covalent, polar covalent, or ionic. And we don't have table of electronegativities, so let's just do it with the periodic table. What do you think? Iodine and iodine. Pure covalent. Cesium and bromine. Ionic. Metal, nonmetal. How about phosphorus and oxygen? Polar covalent. These guys are different, phosphorus and oxygen. Any questions?